Hi, and welcome to the video on Introduction to Rational Functions. We're going to talk about their domains, their vertical and horizontal asymptotes, and learn to identify holes in rational functions. Let's go ahead and get started. All right, a rational function, as the name suggests, ratio, is a quotient of polynomial functions. So it's a polynomial function divided by another polynomial function. And of course, we cannot have the denominator polynomial function be equal to 0 because we cannot divide by 0. So in this first example, we're just going to learn to identify the polynomial function, the rational functions. So we're going to check that there's a polynomial in the numerator and a polynomial in the denominator. So let's try A. The numerator is t squared minus 2t plus 3, and the denominator is t plus 1. Both of those are polynomials, so check. The second one, B, e to the k over k squared plus 1. Nope, e to the k is not a polynomial, so not a rational function. Why don't you guys try C, D, and D real quick and come back. All right, what do you think? Is C a rational function? Definitely not. The denominator is z to the 1/2 or the square root of z. Remember, that is not a polynomial. And D is a polynomial. It's very simple. 3 is a very boring polynomial. And V is also a very boring polynomial, but they both are polynomials. So D is a rational function. All right, one thing we always like to talk about when we introduce new functions is their domains. And for rational functions, the denominator tells us what isn't in the domain because we don't want to divide by 0. The denominator also tells us where the vertical asymptotes occur. And so these inputs that are in the denominator that make the denominator equal to 0 are excluded from the domain, and they are also where the vertical asymptotes occur. Vertical asymptotes occur when we try to divide a number by 0, or anything by 0, and they are usually drawn in as dashed vertical lines, and there's just not an output value there. So we usually write the vertical line as an equation x equals a particular number. We're going to do some examples of this. All right, so let's look at this example for f of x, and let's decide what is the domain of this function, what values are excluded from it, and what are the vertical asymptotes. So to find the values excluded from the domain, we're going to look at the denominator, x squared minus 4. We're going to set that equal to 0, and then we're going to exclude those values. We don't want the ones where this denominator equals 0. So x squared minus 4 equals 0 is a quadratic equation. We can use the square root method to solve it. So let's add 4 to both sides. So x equals plus or minus 2. Both of those values are not in the domain. So what is the domain of f of x? Well, all real numbers except -2 and 2. So in words, we would write all real numbers except -2 or 2. And if we want to put that in interval notation, we're going to go from -infinity up to -2. We're going to go from -2 to 2, not including any of those endpoints. And finally, we're going to go from 2 to infinity. So that is how we write the domain in interval notation. And so what are the vertical asymptotes? Well, they're going to occur at those values in the domain that we excluded. In fact, this solution right here is a solution to a quadratic equation, but a little bit confusingly, it is also the exact format we need for the two vertical lines. So our vertical lines are x equals 2 and x equals -2. So this is an example of when context is really important in mathematics. Up here, x equals plus or minus 2 is a solution to an equation. Down here, x equals 2 and x equals -2 are equations of vertical lines. All right, so let's go ahead and mark these vertical lines on our graph. Here's our function that we are graphing. I just used Desmos to graph it. And you can see the vertical asymptotes here at 2 and -2. It doesn't cross. So let's just draw them in as dashed lines. So there's x equal to 2. And you can see the function gets really close on both sides, but never crosses it. All right, let's look at another example. Oh, no, but let's talk about the numerator. Sorry. The numerator tells us the horizontal intercepts. This is the same as we have, we've been finding horizontal intercepts for functions all along. So this isn't a new feature. So, but we're going to notice that when the numerator is equal to 0, then the whole function is equal to 0 as long as the denominator is odd equal to 0 also at that same point. We'll talk about that at the very end of this video. So right now we're going to look at the points where the numerator equals 0 the denominator is non-zero, so the output is 0. So here's our same example. F of x equals x minus 7 over x squared minus 4. Let's find the horizontal intercept or intercepts, and that's going to be where we set the numerator equal to 0. So x minus 7 equals 0. That means x equals 7. So that's the point 7, 0. And let's go ahead and just find that one on the graph. It's right here. 7, 0, the one horizontal intercept. What about a vertical intercept? Again, this is the same way we found vertical intercepts all along. We're going to put x equal to 0 and solve. So to find the vertical intercept, like with all functions, we just evaluate the function at 0. So that's 0 minus 7 over 0 squared minus 4. So that's negative 7 over negative 4, which is 7/4. And let's mark these on the graph also. So that's going to be right here, 7/4. So this is my horizontal intercept at 7, 0, and my vertical intercept is 0, 7/4. All right, let's try all the stuff we know with the new example. So the new example is t of x equals x over x squared minus 64. So the first thing we're going to look at is with the domain. And remember, we find the exclusions from the domain by finding where the denominator equals 0. So we're going to set x squared minus 64 equals 0. And they're not all going to be square root methods. We just got lucky here. So x squared, add 64 to each side. X squared equals 64. Square root, x equals plus or minus 8. These are excluded values. And I'm just going to draw a quick number line here before I do my interval notation to just remind people how to do that. So here's negative 8, here's 0, here's 8. And our domain is everything up to negative 8, but not including it. Everything between negative 8 and 8, but not including it. And everything from 8 to infinity. So when we go to interval notation, we go left to right. Here's negative infinity and here's infinity. We go from negative infinity to negative 8. We go between negative 8 and 8. And we go from 8 to infinity. Right? So that's my domain. And what are my vertical asymptotes? Again, remember, you are kind of given that answer when you find those values excluded from the domain. It's x equals 8. These are vertical lines, x equals negative 8. What are the horizontal intercepts and the vertical intercept? We should have a little parentheses. There's not necessarily more than one horizontal intercept. So to find the horizontal intercept, that's where we set the numerator equal to 0. Well, the numerator in this one is just x. So we just set x equal to 0. Very easy to solve. So our horizontal intercept is 0, 0. And our vertical intercept, we're going to find t of 0. To find the vertical intercept, that's going to be 0 over 0 squared minus 64, which is 0 over negative 64, which is 0. So the same, obviously, if it's 0, 0, it's both the horizontal and vertical intercept. So let's sketch what we know so far. I'm going to zoom out just a teeny bit here. We're just going to draw a quick graph. Well, we know 0, 0 is the vertical and horizontal intercept. We know at 8 and negative 8, there are vertical asymptotes. So that's what we know so far. All right, I would like you guys to try this example, similar example. I would like you to find the domain, vertical asymptote, horizontal intercepts and vertical intercepts, and sketch what you know, just like similar to what we just did. Pause the video and give that a try. All right, how did it go? Well, let's look at the domain. We want to make x minus 3 equal to 0, so x equals 3. So the domain is all real numbers except 3. There's my domain. So my vertical asymptote, there's only one, x equal to 3. Horizontal intercepts, well, that would be where the numerator equals 0. So that would be where 6 equals 0. That doesn't happen, so there are no horizontal intercepts. And the vertical intercept would be c of 0. So that's 6 over 0 minus 3, which is 6 over negative 3, which is negative 2. So that's going to occur at 0, negative 2. And so let's sketch what we have so far. Well, at 3, we have a vertical intercept, a vertical asymptote, and we cross, the vertical intercept is at 0, negative 2. So that is what we have so far. All right, let's try one more of these, a little bit harder. Again, pause the video, give it a try, and we'll go over it together. All right, how'd it go? Well, let's jump right in. Let's find the domain. That's going to be where x squared minus 3x minus 4 equals 0. Now I could solve this using the quadratic formula. I think I'm just going to factor because I think this factors as x minus 4, x plus 1. So those two numbers multiply to -4 and add to -3. So x equals 4 is one solution and x equals -1 is another one. So the domain is minus infinity to -1, union -1 to 4, union 4 to infinity. So that's my domain. What are the vertical asymptotes? Well, x equal to 4 and x equal to -1. All right, let's find the horizontal intercept and the vertical intercept. So the horizontal intercept is going to be where the numerator is 0. So x squared plus 1 equals 0. You can solve this using the square root method. X squared equals -1. Now, we know how to solve this because we know about complex numbers, but we don't graph complex numbers, don't show up on the graph. So at this point, we put no real solution. There's a complex solution, but no real solution, so that means there's no horizontal intercepts. And the vertical intercept is going to be k evaluated at 0. So that's 0 squared plus 1 over 0 squared minus 3 times 0 minus 4, which is 1 over -4, which is negative a fourth. So over 0 up -1/4. And let's sketch what we know. Well, we have vertical asymptotes at 4 and -1. There are no horizontal intercepts, and the vertical intercept is at 0, -1/4, which I'm drawing there. All right, so let's talk about a little bit more information that we need to find out about rational functions. There's some information that we get from a combination of both the numerator and the denominator. So the first characteristic we're going to talk about is a hole in a rational function. These are also called removable discontinuities. I can't talk today. Removable discontinuities. So these are created when you get a 0 in the numerator and also a 0 in the denominator. That does not make a horizontal intercept. It does not make a vertical asymptote. It is just a hole in the function because of the way they interact together. You can't divide 0 by 0. That is not even defined. So what it does is it just makes a gap in the function. So if we look at this function here, f of x, we can see that at x equal to 2, the numerator is going to be 0, because that's going to be 0, and the denominator is also going to be 0. All right, you're tempted to cancel these because algebraically you can cancel them, but the function is defined that way, so you can't do it if you're actually trying to graph this function. So what that means is that x equal to 2, there is a hole in this function, and you can't actually see it on the graph. If you use just when you glance at Desmos, if you look at it really carefully and you zoom in, you actually can find there'll be a spot right at 2, 0 where if you try to trace, it'll just, I don't know what I did there. If you try to trace on the graph, it'll just have a gap for the y value, but there is a hole right there at 2, okay? So that's one thing that can happen. And the other thing that happens are horizontal asymptotes. And horizontal asymptotes are all about what happens in the end behavior. They don't affect in the middle, just at the end. They are graphed as horizontal dashed lines, and they're always of the form y equals a number because horizontal lines are a fixed y value. So don't forget, every polynomial has a leading term and a degree. And we're going to just look at those leading terms and the degree of the numerator polynomial and the denominator polynomial to think about horizontal asymptotes of rational functions. And here is the rules for horizontal asymptotes of rational functions. So this is definitely something that should go on your note card. If the degree of the numerator is less than the degree of the denominator, so the numerator degree is less than the denominator degree, then the x-axis is a horizontal asymptote, y equal to 0, the x-axis. If the powers on the numerator, if the degree of the numerator is the same as the degree of the denominator, then the ratio of the leading coefficients is a horizontal asymptote. So you're going to look at those leading coefficients and write that a over b, and that's going to be your horizontal asymptote. And finally, if the degree of the numerator is bigger than the degree of the denominator, then there is no horizontal asymptote. So these are a little bit tricky to remember. Be sure you write them down, put them on your note card. And let's look at some examples of these. All right, we'll actually have the rules here so we can look at the examples and look at the rules at the same time. So in example 6, we have g of x, and I didn't even bother to write out the rest of it. These are the highest powers in each of the polynomials. We have 2x cubed plus a bunch of stuff, less than x cubed, divided by 5x to the 5th. So in this example, the degree of the denominator is 5, right? 5. And the degree of the numerator is 3. So that's the first case. The numerator has a smaller degree than the denominator. So y equal to 0 is the horizontal asymptote for g of x. For b, the degree of the numerator is 2, and so is the degree of the denominator. So y equal to negative 14, which is the leading coefficient on the numerator, over 7, which is the leading coefficient of the denominator, is my horizontal asymptote. So I would just write that at y equal to negative 2. And in the last case, the degree of the numerator is 5. The degree of the denominator is 4. So there is no horizontal asymptote. Okay, so that's the 3 ways that can happen. I just squished it in there. All right, so now looking at our graph, just so we know what these look like, which is which here. So the red graph shows, excuse me, a horizontal asymptote of the x-axis. So you can see as time goes by here, it's just going to get closer and closer and closer to that x-axis. So this is going to be g of x, the red function. You can see the blue function, The blue function has a horizontal asymptote at y equal to 2. So that was named f of x. So this one is f of x, and you can see that asymptotic behavior. And so the green function doesn't have any horizontal asymptotic behavior. So this one is going to be my last function, which was named k of x. All right. Well, that's it on the introduction to rational functions.